Afternoon, everyone. Good afternoon, everyone. I'm Dr. Yao Zhang from Northern University. I'm now a senior lecturer in mechanical engineering. And I would like to welcome our audience and speakers to the second event of the IEEE UK and Ireland Women in Engineering UKI Ambassador Program, the Early Career Talk. And I would like to invite Dr. Nagham Saeed to open this webinar talk, please.
Hi, thank you very much, Yao. So hello, everyone, and thank you very much for joining us on the IEEE Women in Engineering UK and Ireland Ambassadors Network. And I would like to welcome and thank you so much. And I would like to thank the ambassadors who helped in organizing this interesting event. This is the second event of the Early Career Talk program. We had a very successful first event on April, and this is the second one. So the aim of this program is to expose the audience to the novel areas and aspects of engineering and computing which solve real world problem, and to establish a link for networking and mentorship, and also a link with the industry, and to create connections for research opportunities. So this workshop hosts researchers who are at different stage of their professional career. One of them is a senior lecturer, the other one is a lecturer, the other one is a newly graduate PhD students with a part-time job. And also we have a PhD student, and she is in her middle journey, in her PhD journey in the middle. So they all share the love for research, and that's why they are here today, to show their remarkable findings and to present their research outcome. So I'm really looking forward to listen to our speakers and their talks, and enjoy a fruitful discussion after they finish their presentation. Back to you.
Yeah, thank you very much, Nagham. So before we start the session, we just a little bit the housekeeping here. So if you want to ask any questions, please use the chat room, and please keep muted when the speakers is presenting. And the audio and presentation will be recorded and later published on the IEEE session website. So also the chat history will not be recorded. So if you want your question to be recorded, please type into the Q&A chat box, and we can address those at the end. And so the agenda for today is we have 4 speakers. So first speaker is Shiva, and second is Kheira, and then Han, and then Mahshid. And then we close the session by Dr. Nagham. So now I'll be handing over to the first speaker, Shiva. Shiva, you ready to do a presentation, please?
Yes, thank you. So just let me know if you can see my presentation, my slides.
Yeah, it's clear.
So, okay. So I'm going to start. I noticed that we are a bit late in time, so without any further ado, I'm going to start. Hello and good afternoon, everyone. Thank you for being here and giving me the opportunity to present my research, which is titled as, well, my presentation is titled as Minimum Energy Efficiency Standard, or as we call it, MEES requirement in the UK. So before I start my presentation, I would introduce myself. As our host mentioned, my name is Shiva Amirkhani, and I'm in the 3rd year of my PhD journey at University of West London. I was born and raised in Tehran, Iran, where I received both my undergraduate and postgraduate degrees in architecture. And then after working for a few years as an architect, I started a course in the UK in health, well-being and sustainable buildings at UCL. And towards the end of it, I was offered a position for doing a PhD at University of West London, which is a collaborative project with Hilton Worldwide and also SIBSI. My project is based on one of the UK government's recent legislation in terms of energy efficiency in building sector, within the commercial sector. And as you probably guessed from the Hilton being one of the collaborative, the specific context of my research is in hotel buildings. So I will now try to put everything in a nutshell and introduce what my project is about. So if I'm pretty sure that you have all seen this sticker, which I have included in the right bottom corner of the slide. You have probably seen it on many household equipment, which shows how energy efficient that device is. Buildings do have the same kind of idea and the same kind of practice applied to them. And this is based on this sticker within the building environment shows how energy efficient that building compared to a benchmark or a target building of the same application. I'm not going to take you through the steps of how these stickers or these certifications are produced, because that's quite lengthy. I will just mention that these ratings are based on the building's CO2 emission rather than just the energy consumption. Before I talk about this, the different aspect of my research and my findings, I would like to to provide a bit of history on how this whole scheme started. For that, we need to go back a little bit in history, where around 1970s, a worldwide energy crisis, which was based on the Middle East area, caused a concern among many European countries about the safe and supply access to the energy, especially among those who were heavily reliant on countries where tend to be politically unstable. So at the same time, there were growing evidence that was showing the increasing role of the building sector in the world's global energy consumption and the CO2 emission. The combination of these two resulted in a new idea in the field of energy efficiency in buildings, and that was the idea of introducing energy certification for building. It took the whole world a few years, maybe a few decades, until it becomes somehow mandatory and legally binding action. So in 2002, the Energy Performance Building Directive, which we call it EPBD, and asked all the European countries to come up with some sort of methodology for calculating the energy performance of their building sector. And based on the framework, the minimum aspects or the minimum energy uses that were meant to be covered through this methodology was heating, cooling, ventilation, hot water, and lighting for each building, but they need to be calculated in a standardized condition. We will get back to this standardized condition later. So it was left to the countries and their the rulers to decide how this methodology should be carried out. This slide just briefly shows how this framework progressed from 2002 until now, which I'm not going through them because it's quite lengthy. So now I'm coming back to the current situation in the UK. So in the UK, these energy performance certificates, which was first, as I mentioned, was firstly mentioned in 2002, is implemented for both domestic and commercial sectors. And I guess, if I'm not mistaken, they started to become part of the national legislation since 2008. But in 2018, the UK government put this measure into a further step and launched the MEES requirement, which stands for Minimum Energy Efficiency Standard, and it targets the energy performance certificate or EPC rating of commercial sectors. If the commercial buildings who need to be sold or rented, they come up with an energy performance rating of below E level, they cannot be sold or rented. And there needs to be measures taken to improve their EPC rating, unless they have already done anything and it's not feasible to do any further measure. If you remember a few slides back, when I was first talking about the EPBD, I mentioned that in 2002 and in the initial framework, it was mentioned that the comparison of the buildings should be carried out within a standardized condition. So in the UK, the bodies that supervise the domestic and non-domestic EPC generation are quite different. For the non-domestic or commercial sector, the supervising body is National Calculation Methodology, or as they call it, NCM. It also provides those standardized conditions or the standard profiles for calculating the energy performance. And as the assessors or whoever is carrying an EPC analysis of a commercial building, there are specific and default values that need to be followed. This is purely for the purpose that, for example, all the office buildings are compared within similar situation, or all the hotel buildings are compared in the similar situation. So far, within the past 3 years that we have been working on this matter, we found several aspects that are somehow can be considered among the uncertainties within the current EPC procedure for non-domestic buildings in the specific case of hotels, which I'm going to very briefly talk about them. The first issue that we found with the current procedure for EPC generating in the hotel buildings is that we noticed that, well, let me tell you this before. You are probably all aware of the potential impact of global warming and the fact that we are experiencing warmer situation, warmer summer, so we expect that there would be a rise in the installation and usage of cooling system, especially within the commercial sectors. In the UK, not all the hotels are currently using cooling system, but it is expected that with the rise in temperature and the hotels' competition over having more guests and providing a more satisfaction for them, there will be a rise in application and usage of cooling system. We carried out the analysis for one of these hotels, and we noticed that unlike what we initially expected, that by adding cooling system to its guest room, there will be a huge drop in its EPC rating. By drop, I mean going for the poorer rating. We found that there is absolutely not a big impact on it, and which was quite a surprise. And then when we took the matter further, we found that this is all down to NCM's unrealistic assumptions for cooling set points. Cooling set point is a temperature that is considered that above that temperature, the cooling system in a space will start working. We found that the current procedure says that the cooling set point for hotel guest room are 25, and that's what we have to follow. But if we want to take it a bit further, we found that for every lower temperature, every 1 degree Celsius lower temperature in cooling set point chosen by guests, there will be a huge increase in the CO2 emission, which unfortunately is not considered in the current procedure. So that's one of the aspects that have been neglected in the NCM guidelines. We provided the result of this research in a study which was published in 2020. Next big issue with the current NCM guidelines in a huge overestimation of hot water consumption. So we have compared 3 existing hotels in the UK, and based at which you can see the breakdown of energy consumption based on the NCM guidelines and based on the NCM assumptions. Almost half of the energy consumption would go for the domestic hot water based on the NCM assumption. But from the experience and from the literature, we know that that's not true. We even compared the data from the simulations by the NCM guidelines with the recorded data from the water consumption of the hotels, and again we found a huge overestimation here. Again, the result of this study was published in 2021. The final point that I want to discuss at the moment is a lack of validation measure. So based on the studies, which accounts to a huge number of studies, not only in the UK, but in all the countries that have some sort of EPC measurement in place, there are a huge body of evidence that when different assessors evaluate the same building, even when they use the similar software for carrying out the simulation, there is a high chance that they will get very different rating. This is because the assessor's subjective assessment has some impact on the result. So this brings us to the idea that for the same building, you can get several different EPC rating, but at the moment, there's no way to decide which one is correct, or which one you need to trust, or which one is a better reflection of the building's energy performance. Of course, from the client's point of view, they will always would go for the one that shows their building in a better energy performance band. But in terms of the bigger picture and in terms of achieving the net zero goals that we have, we need to find out what the actual situation with that hotel or that building is. So this is another problem with the current EPC procedure, that currently we don't have any means of validation of different results for the same building. So the bottom line message from my study was that so the EPC scheme has been quite successful in the past when there was no other scheme in place, but now if we want to actively achieve our ambitious goal of highly reducing the CO2, we need this uncertainty to be sorted. The other thing is that we noticed that this EPC scheme within this existing uncertainties might result in high unreliability among people, both in terms of the clients and the assessors. And that would be one of the difficulties on our path if we want to fulfill our ambitious goal. So that was mainly my presentation. So I will stop here now. Thank you for listening. And if there's any question, I would be happy to answer. Thank you.
Thank you very much, Shiva. I just realized I didn't turn on my camera. Sorry about that.
Okay.
It's really good presentation. And I've got one question to ask. Do you think there's any differences between the EPC scheme for the domestic buildings and non-domestic buildings?
Well, as I mentioned, yes, there are differences in terms of the supervising bodies, and the whole scheme is somehow different, even in terms of the rating system. Well, both of this sector rely on the amount of CO2 emission to rate that building's energy performance. But the software that you should use and the sort of I don't know, the default values are totally different, and even the supervising bodies are completely different. So they are not literally that much comparable. So because they are intrinsically different.
Yeah, right. Thank you for the answer.
There's questions from the audience here. There are 2 questions from the audience, if you just want to read them.
Sorry.
Read them. Is there any consideration?
Sorry, I'll ask them directly if you want.
Yes, please do. Thank you.
So I had 2 quick questions. I'm sorry if you've already answered this. I didn't think so, but I may have gotten wrong. First, what consideration as to how the energy was created? Because I don't know, maybe would that be helpful to find out? And the second question then was, this sounds really good. So how do we encourage people to actually take this on board, to note the change? Is there sanctions we can apply? Because you did mention that these are directives which are then being applied as national laws and regulations,
calculation.
we encourage that kind of change?
Yes. So yeah, so in terms of the first one, your first question, Eve, I guess it was, you meant how these are rated, or like, did I get it right?
Well, if the energy, I'm more from the data center aspect, and we try to take some of the heat that comes off our data center and then feed it back into heat rooms in the building.
Yes.
So that would help us in that we're using existing heat and it's more an energy friendly way. So does that get carried in the new measurement techniques?
Yes, yes. So when you need to get an EPC for your building, and I'm talking about the non-domestic buildings. So when an assessor comes to do that, he or she needs to carry a full evaluation of your building and checks not only like the building fabric specification in terms of what's the material in this building, how is the glazing, or this kind of a specification, but more importantly, the heating system, the cooling system, or is there any heat recovery system in that building? All this information will be fed into a specific tool, and then based on all this information and based on a benchmark, which is somehow again is related to the type of your building, the energy performance of your building will be announced compared to that benchmark or to that target level.
Thank you for answering that.
Okay, and the next one, I guess you asked about how we expect people to onboard this. Am I right?
Yeah.
Yeah, so as I mentioned, since 2008, both domestic and non-domestic EPCs have become mandatory. So if you want to, again, I'm not sure about the each aspect in the domestic, but in the non-domestic building, when you want to rent out or sell your property, you have to have this EPC rating, and you need to redo it and reevaluate your building every 10 years. But in the meantime, in between these 10 years, if there is any specific change to your building, whether in terms of the application or usage of the area, or in terms of the changes to the heating system or cooling system, you need to renew this. But currently, it is like part of the national regulation that if you want to like do any sort of selling or renting, you have to have that EPC rating, otherwise it just cannot go through.
That's great. Thank you.
No worries.
Thank you, Shiva. That was very interesting. I've got one question also. So you mentioned the NCM, the National Calculation Methodology. So why do you think this guidance, why it exists? Why does this one exist? And why it is necessary for us to follow it?
Well, as I mentioned, like the framework, which was initially launched in 2002, mentioned that there should be some sort of a standardized situation so that buildings of similar type, like for example, office building or hotel buildings or supermarkets, can be comparable to each other. For providing that base of comparison, we need to have this sort of a standardized situation, and by this standard we mean that, for example, we consider that in all the hotel guest rooms, the rooms will be heated up to the temperature of 21, although in reality that might not be the case. But because we need to have some sort of base for comparing the building of similar type to each other, we need to have that kind of a standardized condition. So in the UK, for the non-domestic building, NCM is the body that provides this standardized condition for us, and purely for the means of the buildings from similar type to be comparable to each other, we have to follow these standardized condition by NCM.
I can see that you published your findings in very important journals like Sustainability. So what is maybe the highlight of your research so far? What is the kind of the big contribution that you think it will add
Well,
to the field?
the thing is that based on the findings, we found that okay, so so far we know that at least in terms of the hotel buildings, we have a huge underestimation of one of the energy uses, which is the cooling energy, and we have a relatively huge overestimation of domestic hot water. To which degree these two uncertainties balance each other, we are not sure because we do not have data. But so far we know that there are at least two huge count of uncertainty involved in the current procedure. That means that even if every other measure is taken to ensure the reliability of an EPC for hotels, there are these issues that might reduce its truthfulness. So that's one thing that in future, and the problem is that when these EPCs are with this uncertainty, you cannot rely on them. And then when you have plans on the paper that in 10 years time, we will reach this level of CO2 emission savings, but in reality, because of all this uncertainty, we might fail to achieve them. So these are among the main findings of my research, which obviously, but there's another one which is under review, so that's the most important one. So I cannot
Thank you very much. Thank you. That was very interesting. Thanks.
No worries. Thank you for your time.
Hey, thank you very much, Shiva, for your presentation and answering the questions.
Thank you.
So I'm now handing over it to the second speaker, Kheira. Kheira,
yes,
could you please share your screen? Yeah.
Yes, hello. So
Yeah, I can hear you.
Yeah, okay. Can you see my screen now?
Yes.
Yes.
Yes. Okay. So hello everyone. So delighted to join you in this event, and thank you very much for giving me the chance to present my work named SMILE for Self-Controlled Mobile Intelligent Low-Cost ECG. So I will be starting by presenting myself. I'm Kheira Lakhdari from Algeria. I hold a PhD in telecommunication systems and networks. My PhD thesis was about building a mobile intelligent platform for the monitoring of chronic diseases. I'm teaching now at Belhaj Boushaib University of Ain Timouchent, Algeria. My research interests include wireless networks, biomedical engineering, intelligent systems, cloud computing, and quantum computing. So before starting, I will present my plan for this presentation. So I will start by a brief introduction, the state of the art of digital and mobile health solutions. Then I will emphasize the most common problems encountered by researchers in this domain. I will then present my solution, SMILE, its results, the followed steps for its validation and ameliorations, and by the end, I will present some of my scientific contributions related to SMILE and a brief conclusion. Today, health status is dramatically evolving with these scary numbers of chronic conditions that increase the speed of infectious diseases like the COVID-19, the one we live with today. So in the other side, technology is remarkably evolving, introducing biomedical engineering, wearables, and sensors advancements. The interconnection of massive and huge amount of data, and the conception of wide networks relating all kind of things in addition to human beings and so on, which is called the Internet of Things, and treating the communicated informations with means of artificial intelligence, which can really generate some very important decisions in all fields. So the patient journey is now much more enriched, but it is really sufficient. We will see during the presentation. So in this context, many scientific and industrial research are evolving every day to propose all kind of digital and healthcare solutions for the monitoring of a wide number of chronic diseases. But it is actually still not very sufficient. Why? Because first of all, those solutions or most of these solutions are trying to meet a high level of efficacy, which can increase automatically their complexity while being used by the patients, while logging and monitoring all these functions on the mobile phone or the application, the proposed application. Things can be really very difficult for non-tech savvy people or for elder people. So it can be really a very complex task to manage. Also, it manage or it handle very sensitive and personal data, which is really very critical and a huge concern for users and patients in general. Also, because of differences between environments, societies, sexes, ages, and so on, it is generally a hard task to develop a solution that can be adopted by everyone, or at least most of the targeted users. So, which may conduct the patient to experience very bad situations while experiencing these solutions. So we will try now to talk about the medical experience or the medical journey of patients. Generally, patients experience pain, fears, uncertainty, lack of confidence, and many other problems during their medical journey. Also, and specifically for cardiovascular diseases, the abnormality may be actually so obscure, so which can be or which can conduct to a subjectivity from the part of the patient while while speaking with his doctor, while consulting his doctor, and also the lack of adaptation, the delays, the late deliverance, the insufficiency of materials, and the high costs of medical services or the generated medical services. So for the cardiovascular diseases, the abnormalities may be obscure. Actually, the electrocardiogram, which is representing the cardiac activity, can be really very different between individuals, which generate a large amount of data that can be highly affected by noises and artifacts. So for that, my solution, Smile, is actually based on a simple Bluetooth application, Bluetooth connection between a novel prototype of the ECG, of the electrocardiogram device, and the mobile application. So this application can read, write, and analyze data with means of artificial intelligence algorithms. When this algorithm detect a urgent situation, so considering a urgent situation, this application can generate automatic notification to the user, the doctor, and the caregivers. So the caregiver or the doctor can access to the data of his patient and can confirm or decline this urgent situation. Also, the platform is also equipped by intelligent systems to monitor the level of battery, the connectivity status, the level of energy, and so on. So, as mentioned before, SMILE, the main platform is composed of the medical sensor and an analytical part. So this is the medical sensor, which is the ECG, and an analytical part. This analytical part is composed of the intelligent algorithm, which are the AI or the artificial intelligence algorithm, and two mobile applications, one for the patient and the other is for the doctor. So the patient, so this is the prototype of the electrocardiogram device. So actually this is the main structure of it. So the whole system can detect actually 5 abnormalities. Between these abnormalities, there is the very critical one, which is called infarctus or myocardial infarction, which can actually conduct to a sudden death. So talking now about the intelligent algorithm, they are composed of deep learning algorithms, which are called convolutional neural networks, or simply CNN models. And also now I will try to simplify the concept of the mobile application. So, so the patient application um, can receive the data from the sensors. It can analyze, read the data, and then analyze them. So analyze it, sorry. So and stock it in real time securely via cloud. In case of an abnormality, so in case of abnormality, there will be some kind of alerts or notifications send it automatically to the doctor, the caregiver, and also displayed on the screen of the patients, the mobile phone of the patients. Okay, so once the SMS, the pre-written messages is received from the doctor can actually check the data of his patient via a login, either to confirm or to decline the generated decision, which 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 can really help him to decide whether which action to be or which procedure to follow. So the detected abnormalities, as said before, are 5, including the very critical one, the myocardial infarction. So this is about the mobile application of the patient, and once receiving the SMS from the doctor can also access to his pre-written messages list to send or to choose one of them and send it to his patient to direct him and guide him to the best action to do. So this is why I name it SMILE, for self-controlled, mobile, intelligent, and low-cost ECG. The results of the proposed algorithm are very promising. It was achieving 99% of precision and accuracy compared to just 96% in the literature. Also, the mobile application was actually having many features like the identification, the authentication, the animations, the Bluetooth connection, also the interpretation of the ECG in real time, the classification of the ECG, and also the generation of real-time alerts. As you can see here, this is an example of generated alert, which was really sending and receiving exactly in the same time. For the validation of Smile, I was migrating it on a mobile environment and tested again with cardiologists to test the performances on new and real ECG data. So actually it was achieving again a big performance. It was achieving 99.3% of accuracy on new data. And also it was really very good performing cross-platform, very compatible with a wide range of mobile phones, and also it has a very light size, and it works really in real time and generates good results in exactly in the same time in case of a urgent situation. So Smile didn't stop there. In order to make it more adaptable and increase its easiness, adaptability with elderly people, with non-tech savvy people, with children, and visually impaired persons, I was thinking about adding some more features, or to adapt the main features of Smile to these categories, while introducing two main techniques, which are called gamification and voice assistant, or the chatbot. So for an example for the gamification technique, so the concept or consists of building a game version to facilitate the concept or the experience for the user. So in this case, it was especially it was especially giving the user the the possibility, or the possibility to put the electrodes of the ECG in the good way. I mean, if he puts the electrodes in the wrong way, so he will end by losing the game. But if he is approaching to the right way of putting the electrodes and making everything works fine, so he will win the game. The bird will be liberated, and everything will be good for him to start using the application and the ECG. So Smile actually was giving me the chance to many interesting scientific contributions. The artificial intelligence parts was developed during an internship at the Canadian University of Dubai, and also the gamification part, the last part, was developed during an internship at the research center of biomedical engineering at Barcelona, Spain. So for the conclusion, I can say that the mobile health is a large domain with a high potential. Smile represents a novel approach of mobile health services. So it mixes a wide number of advanced technologies. It can be an excellent assistant for the healthcare professionals, and it can give a better help to patients, and elderly persons. So thank you for listening, and you are welcome for any question.
Yes, thank you very much, Kheira. I think in the chat, uh, Rose has
Yes.
sent some questions. You want to so in the chat is the speed of the access to relevant information is great for the patient. And the question here is, did you have any security concerns when designing the system?
Yes, actually, the security concerns was the very first concerns about the platform, and then the procedure was by adopting some kind of pop-up notifications to the patients to allow or decline the access, and also with the login and the authentication parts for the healthcare professionals, either to access to the cloud or the patient data, or also to send the pre-written message to the patient.
Right. Okay. Thanks for answering that.
Okay.
Another question from me is, most healthcare professionals, they seems don't trust digital solutions like artificial intelligence or deep learning or machine learning. So how did your solution convince them to adopt it?
So actually, to respond to this concern, actually Smile is not a very standalone application. So it can generate medical decisions, but the generated medical decision must be confirmed in real time by the healthcare professional before being proceeding, or before accessing or having the chance to do any medical action. So there is always the step of the medical confirmation from the healthcare professionals before proceeding to the medical action.
Okay, yeah. Thanks for
Yeah.
answering that. Any other
Thank you.
questions?
Thank you, Duka. Thank you. Yeah. I've got a question, if you don't mind, Kheira. You
Okay.
set your objectives in the beginning, and while you were designing this solution, just to have it like a product which is user friendly, and I am interested in that field, in the intelligent system field. So did you achieve your objectives? Did you set a system which is different than the systems which we can see, or the solution which are available for mobile health? So did you achieve that goal? And what is
Yes.
the remarkable bit about your system?
Actually, for achieving these goals, actually it is achieved, but partially. So I'm still working on achieving it. I'm always working on ameliorating the gamification and the part that can give the application more more friendly vision. So, what is the remarkable thing about Smile is the adaptability part. I mean, the generated messages for the patients are written in a different way from those sent to the doctor. I mean, for the doctor, we use very precise and medical language, but for the patient, it is more about encouraging him, about guiding him, and also the gamification part, which can help him to put correctly the electrode, which is really very hard task, and also the most the most targeted problem in the scientific research. because I mean, if the electrodes are putted wrongly, so that means that all the measures or all the numbers can go wrong, and then the medical decisions can be wrong, and so on. So if we put the electrodes in the best way, we can achieve more accuracy and more precision. And then helping the user with a friendly manner to put the electrode with the game,
Yes.
like encouraging him is the best part of
Yeah,
Smile.
training the
Yes.
users from home. Yeah, that's very interesting. Yeah, thank you very much.
Yeah.
Thanks.
Thank you very much.
So I have a question, please. So is the system flexible enough to change the parameters from one patient to another? So if a patient needs to measure the heartbeat, the pressure, the blood pressure is different from another one who has Alzheimer's. So these things, and then it can get the notification to the doctor according to the patient situation.
Yes, actually for Smile, so the goal is that, but actually we're still working on covering all the sites of patients of the patient journey. I mean we started only with the ECG. So the
Yeah.
electrocardiogram, the cardiac activity is somehow different from the blood pressure and so on. So
Yeah.
adding more features mean that we gonna use more parameters, and this can increase somehow the accuracy of the system. So we still work on covering more and more sites of the patient journey. Yeah.
Okay, thank you. So this would be very helpful to be like a
Thank
future work, so it can be cover all the symptoms
Yeah.
of all the patients. Yeah, thank you so much.
Yeah. Thank you very much.
Okay, thank you, Kheira, for the wonderful presentation and answering the questions.
Thank
So
you.
let's welcome. So let's welcome the third speaker, Han, who is also my colleague in Luxembourg at the university, and we both work in the Department of Mechanical. So Han, please go ahead.
Oh, can you hear me?
Yeah, it's clear, and I can also see your presentation as well.
Yeah, okay, great. Thank you. Yeah, hello everyone. Good afternoon. It's my great pleasure to share my recent research on rainbow materials for broadband multi-frequency range vibration attenuation with you. I'm Han Meng, as Yao has just introduced. I work at Northumbria University. My research is mainly about design materials and structures for noise and vibration control, such as lightweight structures, foams, porous materials, and matte materials, etc. So let me introduce a little bit background on this topic. So elastoacoustic materials are actually engineered materials that exhibit some acoustic and elastic responses that can't be achieved by conventional materials. So they actually possess some Euro properties. So one of the most important Euro properties is band gap. So a band gap is a frequency range within which the propagation of acoustic and elastic waves is prohibited. So with this band gap, we can actually achieve very good noise and vibration attenuation. There are actually two mechanisms for this band gap: backscattering and local resonance. So backscattering is that if we have a wave, that the wave meets two different particles, and each particle will generate a wave. So these waves might have different phase. So if the two waves are in phase, that they have the same phase, the resultant force of these two waves, the amplitude of the resultant force will be greatly increased. And by contrast, if the two waves are out of phase, that they have the phase difference pi, that the amplitude, the resultant force will become zero. So a band gap will form. So you can see that in order to achieving these backscattering band gaps, the phase difference of the two waves should be zero, should be pi, so that the distance between the two particles should be equal to half of the wavelength. So this is local resonance band gap. Assume we have a structure, a mass spring oscillator is attached to this structure. That we know that at the resonance frequency of this mass spring oscillators, that the oscillators will vibrate, but the structures, the vibration of the structures will be replaced by the vibration of these oscillators. So it's like that the vibration energy is absorbed by these oscillators. So this phenomena, we called it local resonance band gaps. So apparently that's, as I have just explained, that the backscattering, they requires the distance between the two particles, that is the dimensions of the lattice, should be equal to half of the wavelength. So at low frequencies, we know the wavelength is very large. So in order to achieve these backscattering band gaps, we should have very large structures. But as to the local resonance band gaps, since it's caused by the resonance of the oscillators, so it can occur at very low frequencies. So that's why we usually, for the low frequency vibration attenuation, we usually adopt this local resonance band gap. Actually, numerous elastoacoustic materials have been proposed. They are composed of fundamental building components, and additional mechanical oscillators. For example, the very first of these acoustic materials is actually they contains that a hard core and soft coatings of the oscillator, and also there are some membranes as springs, and some attached platelet can work as mass. So this is also oscillator, and also there is the very famous Helmholtz resonators. An array of Helmholtz resonators can form a negative effective modulus acoustic material. And also there is a tube with side holes which can show the negative effective modulus properties is also type of material. And also there are tubes with both side holes and membranes. So except this one, in an effort to develop the real world materials for industry applications, many researchers also developed some materials with engineering structures. For example, the materials composed of beams with resonators, plate with resonators, and also the widely applied sandwich structures with resonators is like this. So most of the proposed material are actually periodic structures. The width of the band gaps is very narrow for practical application. The worst case is that the lower the band gap frequency is, the narrower the bandwidth is. So that's why we developed non-periodic rainbow materials with spatially varying resonators that aim at broadening local resonance band gaps. So this is our designed rainbow material beam. And this is pie-shaped beam. A parallel plate works actually partitions these beams into different units. So why we investigated this host structure, because this structure can be easily extended to the sandwich structures, which are very widely used in many engineering areas. So this is a backbone, and we actually and attached to the backbone structures as a cantilever mass resonators is like this. There are two columns of these resonators, and the mass of the resonators can vary along the beam. So we can have spatially varying rainbow-shaped resonators. And besides, in each unit cell, since there are two resonators, the two resonators, they can be symmetric or non-symmetric. If they are non-symmetric, we will have multiple frequency range band gaps. And we set up an analytical model to evaluate to calculate the frequency response functions of these material beams. I will introduce this our theory briefly. The first, we calculated the interaction force between the resonators and the host beam is like this, based on the shear force calculation formula. And then we calculate the we relate the displacement at different unit cells based on the transfer matrix. And then we assume that if there is a force excite the beam at one end, and we can calculate the beam at the other end. And with this excitation force and the displacement, we can calculate the receptance functions, which is the displacement frequency response function of this material beam is like this. We conducted experiments to validate our theory. So we manufactured some samples by additive manufacturing method. So this selective laser sintering is one of the most popular additive manufacturing technology. So for this this method actually used the powder to create these samples. The powders, they are put in a chamber and then they are transferred to this moving plate. So a laser is used to sinter this part layer by layer, and then finally reach our designed samples like this. And these manufactured samples are tested with this dynamic testing system. There is the beam was excited by a mechanical shaker at one end. A sensor is also attached to this beam to measure the actual force on this beam. And at the other end of the beam, a vibrometer was used to measure the displacement. And then the measured force and the displacement was then sent to a junction box and then processed by this computer to calculate the frequency response function of the beam. This is a picture of the mechanical shaker and the samples. So this is a comparison between the measured results and the analytical results. So in these sub-figures shows the distributions of resonant mass, the change of the resonant mass along the beam. So we can see that we manufactured 5 different samples. So basically we can see that the analytical results are actually generally in good agreement with the experimental one. There indeed some discrepancies, mainly for example, such as the frequency of the band gaps. These discrepancies we think might be attributed to the physical parameter or variability of tested samples, as well as the uncertainties introduced by the manufacturing and experimental conditions. For example, since the additive manufacturing, they created the structures layer by layer. There are some pores, small pores, very small pores, and defects introduced during the manufacturing process. So there are some discrepancies, there are some variabilities of the physical parameters are unavoidable during these processes. So that's why we said that these discrepancies should be related to this physical parameter variability. And now after the validation of our theory, we can use our analytical model to explore the influence of the rainbow resonators on the material beam. So this is a comparison of the 3 material beams with different resonators. The 3 beams, they have the same host structure, and the total mass of the resonators is about 20% of the host beam. The difference is that one of the beam, they actually have periodic, it has periodic resonators along the beam. Another one, it has linearly varying resonators along the beam. And the last one has sinusoidally varying resonators along the beam. So by comparison, we can see that compared with this periodic material beam, this non-periodic material beams actually have wider band gaps. So we think that the rainbow-shaped, these non-periodic rainbow-shaped resonators can introduce inertial forces inside a broader frequency range. So the bandwidth is thus enlarged. And now let's look at the material beams with non-symmetric resonators. As I just explained that in each unit cells, the two resonators can be either symmetric or asymmetric. If this is a comparison of the two situations, that is, for these symmetric resonators, the mass of the resonators is about 20%, of the mass of the host beam. And for these asymmetric resonators, one columns or resonators, they have a mass about 50% of the backbone structure. The other columns of the resonators, they have like 50% mass of the backbone structure. So we can see that in this considered frequency range, the material beam with symmetric resonators, they have one band gap, but the other beam with non-symmetric resonators have two band gaps. So what is this? So why there are two band gaps for these non-symmetric resonators? We can check from the displacement, this color figure for this displacement. For these figures, the x-axis represents the distance along the beam, and the y-axis represents the frequency, and the color represents the displacement. So this is the displacement of the backbone. This is the displacement of the one set of resonators with a mass of about 50% of the backbone. And this is the resonators, this is the displacement of the other set of resonators with a mass about 5% of the backbone. So we can see clearly that there are obviously two band gaps in these backbone structures. And at the first band gap frequency, we can see that this set of resonators with a mass of 50% of the backbone structures have very large vibration. And by contrast, the other set of resonators with 5%, with a mass about 5% of backbones, they actually don't vibrate at all in this band gap frequency range. So which means that the first band gap is caused by this set of resonators. And if we look at the second band gaps, we can see that within these band gaps, this set of resonators with 50% mass, they don't vibrate, but the other set of resonators, they vibrate very largely within this frequency range, which means that a second band gap is caused by the other set of resonators. So that's why we can achieve multiple band gaps with non-symmetric resonators. And also we can check, this is a comparison between the materials with non-periodic asymmetric resonators and material being with periodic but asymmetric resonators. So we can see that the resonator mass distributions like this. This is the periodic beam, and this is the rainbow beam. So we can see that the band gap frequency is also greatly enlarged compared with this periodic beam. So which means that we can achieve broadband multi-frequency range attenuation by the beams with non-periodic rainbow-shaped cantilever mass resonators. So this is the conclusion that we can know that the rainbow material, the non-periodic materials, can have broader band gaps than periodic structures of the same mass. And also the multiple band gaps can be achieved with asymmetric resonators. Yeah, this is basically my presentation today.
Right. Thank you very much, Han, for the informative presentation. I think Nagham, you got a question you put in the chat. You want to ask yourself?
Yes, that's right. That's right. Yeah, thank you very much.
Yeah. So okay, the first question is.
So just what are the application which the meta material can use for? So you are talking about the rainbow meta material, just which can support the broadband, so what are the application which you recommend for the rainbow metametal to be used for? I saw later on, of course, the autistic but is that the only area?
No. Actually, there are lots of potential applications for our design material. As I just explained, that our structure can be easily extended to sandwich structure. We know that sandwich structures nowadays is very popular engineering structure that is used in like airplanes, like in cars, like in high-speed trains or other vehicles. So our targeted area is trying to apply the concept of this our rainbow design to these materials that in the vehicles and other engineering areas.
Can you add the vibration bit? Is it just to kind of for you to validate your results and to analyze your results? So just the shaking bit to show the interface, the interference between the bands. Is that right? The vibration.
I beg your pardon. I don't understand your question very well. You mean
so
that
what's the purpose of the vibration? Why the vibration is apart from your design?
Yeah, because this material is designed for the vibration attenuation. Because in our real life or in other situations that we know that there's some noise and vibrations. That is not unnecessary noise and vibrations that can bring damages to our health, bring damages to our system, to our structures. You have the experience if you're in the airplane, you feel the noise is very annoying. That's not good for our health. So our design can actually reduce the noise and the vibration level like this.
Yeah, I think
trying to unmute my mic. Sorry about that. Yes, I think you confirm my question. Yes, so you are putting here the vibration just to emulate the noise. But do you think the next stage will be just to trying to implement your theory with real application to see if the noise is different and you're going to get a different results?
Yes. The next step of our work will apply the structures I designed to the real situation, to real life. For example, as I said, to the high-speed trains, to the airplanes, to replace the current. For example, the current holes, current cabin walls, to replace these things. That's ideal situation that I can do that thing. It will be great. Yeah, this is our target areas.
And my last question is just you did adopt a linear and sinusoidal distribution for the resonance. So any special reason for that?
Oh, sorry, let me show. Yeah, because no special reason, because the linear distribution and sinusoidal distribution are actually two very basic non-periodic distributions. The other complex distributions can actually pile up based on these two distributions. So that's why we choose two very simple distributions as our first step, as our first exploration. And actually, after this work, we have started working about the optimization of the distributions of the resonators. That is, we try to find the optimal distributions. This linear or sinusoidal, we can't guarantee is the optimal. So that's why we need to do some optimization work.
And another one before I pass to the other speakers. So you talked about the symmetric and the symmetric rainbow. So which one you think it can give better results, or each one will have its own?
You mean this one? That is
yes,
which one?
Yes.
Yeah.
Based on what?
I can't say which one is better, which one is not. It depends on your requirement. For example, if your noise source is only within one frequency range, that the symmetric resonators can definitely work. But if you have noise or the vibrations within multiple frequency range, so for this case, we need to design these non-symmetric resonators. So it's hard to say which one is better. It just depends on your requirements.
Yes, thank you very much. Thanks a lot. Very interesting.
Thank you.
Yeah, thank you very much, Han, for the presentation and answering the question. So let's now welcome
I think Ruth, you've got a question here.
All right, sorry. So, Ruth, you got a question you would like to ask?
Yeah, I'll make it fast, although I'm not sure I even know how to phrase the question, so apologize if I get this wrong. So there are a lot of small parts and angles. There's a lot to it. It's actually kind of complicated structure. And therefore that makes me think it could go wrong. Wear and tear over time, poor manufacture. What's going to be the impact of that? Or have you looked at the impact of that with regard to an impact on the quality? Any noise distortion that's caused by poor production quality?
You mean like there's some defect introduced by the manufacturing, like the additive. Yeah, actually, and for this is a very good question, because we actually measured the influence of for example, as I said, there are some variabilities, there are some uncertainties introduced by this additive manufacturing. We manufactured multiple, like we manufactured like 20 samples and test how the additive manufacturing affect the physical parameters. We find that, for example, about the density of these structures actually arranged, like they have a difference about 3%, but the elastic modulus, they can have a discrepancy as about up to 10%. So yeah, as you said, that there are actually some, if the discrepancy of the variables and uncertainties of these parameters, they can be very large. For that case, we need to consider this during the design. That's actually a good problem. Yes, we need to consider some, because sometimes the physical parameter variabilities can be very large.
Okay, thank you.
All right. Thanks, Han. And then we move to the last speaker, Mahshid, please.
Last but not least.
Hello.
Yeah, I can hear you.
Yes, Mahshid, we can hear you.
All right, I'm going to share my screen now. Okay, so hello everyone. My name is Mahshid Yazdi, and today I'm going to talk about the sustainable design in biomedical application. I'm going to give you a little bit introduction about myself and my background. So what I study, what was my work background, and how I end up my research area in sort of a sustainability in design. So I did my bachelor degree in material engineering, when we study about different materials and sort of a manufacturing process. And I did both my master and my PhD at Brunel University in London. My master degree mostly was in biomedical engineering, and my PhD was in mechanical design, especially in biomedical engineering and structural design in implants. Then when I was a PhD student, I was working as a teaching assistant at Brunel University, and then I moved for a year at Uxbridge College to do a lecturing and teaching. Then I did my postdoc at Birmingham City University, which was about a structural design and a safe working load for the correct structure. And then with the sort of the same company I was working at Birmingham City University, I became a head of research and development at the company for developing a further structure in the heavy packaging especially. And then I moved to, 4 years ago, I moved to Coventry University as a lecturer, and I decided to come back basically at the academic and research. So all my background was sort of a structural design and biomedical and design engineering, plus material and the manufacturing brought me to thinking about sustainable design and apply it in my research. Give you a little bit of introduction about the sustainability in design. The sustainability in design, it's based on the triple R, we normally say, which is reducing, a material. So if as a designer you're looking at some products, you should be able to think whether you can reduce any material, or whether you can reduce the volume of the material, or reduce a part which is not necessary. So it is basically either is a redesigning, or either it is a new design. So you have to always think about reducing parts, material, or unnecessary things that is not really looking for the function of that product. The second R is the recycling. So looking at the material which are recyclable, or looking at the design in terms of if you can make it basically separate based on if you got some parts and you sort of assembling them together. Think about whether it's possible to disassemble and so sort of deselect the parts that are not recyclable. So then by that design, you can separate the part which is recyclable and send it for a recycle system. So that's the things that you have to think in the design as well. And the last one is the reuse. So reusing, it's these days, I mean, if you're looking at design for a new mobile phone, and you can't really, if the battery for some reason start to not working properly, and if you want to change it, it's not possible. And I mean, previously few years back, something you could buy a battery and sort of changing it. So this calls the reuse in design. So if some part doesn't work, you can either replace it, so you are able to reuse some the products as well. But if new mobile phone, you're looking at them, because it's mostly running by business the companies, rather than a proper engineer. So it is now been sealed, because they want to, when anything goes wrong, you just put your mobile phone in a bin or send it for recycling and then buy a new phone. So this is, I mean, a simple example regarding your mobile phone, but a lot of things that is these days is moving toward not reusing them, which is as a designer, we are using, we should think about designing a product which is possible to, if something goes wrong, it can be replaced and reused again and again, rather than sort of putting it to the bin or destroy them. So this is the triple R that's as a designer, when you want to do the sustainable design, we look at. In this sort of a design, it's moved me to looking at the lightweight structures. So in recent years, new structures have been developed for sustainability, as they are lighter with less material usage, while sustaining their mechanical properties to be utilized in the applications. After like a revolution of the 3D printing, a lot of structures or the shape which was not possible to manufacture previously, it was possible to manufacture them afterwards. So a lot of scientists thinking, okay, when we say about the sustainability design, we are the one things was reducing. So using some lightweight structure, when they can handle the proper pressure or the load they are supposed to handle, that could help the design for reducing the material usage, rather than having a sort of a solid blocks. So here, I mean, in this slide, you can see that there are hundreds of different structure, but there are some common nanostructure that it's used in material and in a sort of a structure of material, or nanoscale structure of the material, like a lattice structure. It's triangular, it's some of them are hexagonal hexagonal structure, some of them are improved hexagonal. I mean, not, if you're looking at the E here, it's like a improved hexagonal structure. These are the triangular structures, and this is cubic structures. But looking at those nanostructure give us a sort of a thinking that those could be improved, developed, and to be used in a different either biomedical application, automotive application, and aerospace application. And basically my research area is looking at the structure, looking at the different parameters of those structures, and looking at the boundary conditions of the application, that whether it's automotive, whether it's aerospace or the biomedical, and applying and calculating whether they are possible to be used or to be replaced, or they need some improvement, or in which part they need the improvement. It might be a small part in those sort of applications, or it might be a small changes, but even sometimes those small changes would help a lot for the planet and for designing in a sustainable way. This is a sort of a, if you're looking at the nanostructures of the foam, and regarding the previous slide that I was explaining, this is Ashby's chart to show the mechanical properties of especially the compressive strength via the density of different foams. These foams is you can see that different foam structure will give different mechanical properties for a different structure, and this is give us an idea that how those nanostructure can be implanted in the millimeter structure and be used in a different application to first reduce the material, second able to handle the function that they are supposed to do. So in my current year's research, me and my students, we were looking at basically two basic structure and few more structure, but I haven't, I'm not going to present it in this presentation, but I'm going to today mainly looking at the honeycomb, which is very common, and the corrugated structure, which is sort of a double honeycomb structure, and compare them and give you an idea how those sort of things work. In the next few slides, I'm going to quickly looking at like automotive applications and the aerospace, and then moving to biomedical and the human interaction application. So if you're looking at this two structure, we apply automotive boundary conditions because it's mostly for a shock absorption. In the automotive, when we use the structure, it is for absorbing the shock, and to look at the boundary condition and to look at the final result, how those structure will respond to shock absorption by looking at the force displacement to see what will happen to the stiffness of the structure. And here, based on the direction of the forces and based on the geometry of a structure, we got a force and the displacement, which can see that the highest toughness and the less stiffness, it's for the corrugated structure, and it is quite a difference because of the direction of the loading conditions. Moving to aerospace application, then we got particularly looking at the wing structure, and we say it's a counterwheel beam when it's fixed from the one end and there's a uniform load applied, to look at what is the stiffness, because we're looking at sort of a certain stiffness for the structure. It's showing us that there is a high toughness but less stiffness for a honeycomb structure if we compare it with the previous slide, because the geometry change in here, and also the loading condition, the direction of loading, because those structures are sort of a composite material, which they give us a different mechanical properties in a different direction. So looking at those structures, looking at the parameters, giving us the idea, it depends on what application we are going to use and what parameter we need to apply to make them useful for the particular application. application. So it means that they can be used and they can be replaced by the solid blocks or the different structure that is currently used, and they sort of saving weight, and they are fit for the functioning requirement that they need to handle. Moving to the biomedical application and looking at the implant application, which is the main function is reducing the stiffness, which is also what is really fit when we say reducing the material as well. If those material could reduce the stiffness as well, that would work for the biomedical application. Here it's showing the both corrugated and honeycomb having a sort of similar stiffness properties, but they are much less than the solid structure, which would help the function of the implant. Plus, it would save a percentage of the material which is used, and especially in the implant when we are talking about the titanium, we got limited resources in the world. So if we reduce the material, because a lot of materials we got limited of them and they are not produced anymore, and if we run out of them, so if we help to use less, we help the environment, we help the planet, and we also help the future generation. We just need to find out the right parameters and the right shape of the materials, of the structure. This is sort of a simple analysis to the basic, the phase 1 analysis, to looking at what is how is the failure when we talk about the stiffness. Okay, that is one parameter, but how those material would fail, and do they need to be changed, and do they need to be improved, in which area they are failing, and do we need to changing the cross section, or do we need to apply a different direction or adding more support to our material. So this is showing us that it's not only the stiffness is important, but the failure analysis that we are running for each sort of application, it is important too. One of the current research that we did, it was using with one of the companies who are using helmets, and we try to build up using a corrugated structure to build up a helmet. The company used a solid polymers, and we try to reduce the weight, and using the corrugated structure by first implementing the phase 1 to looking at what are the parameters, what are the thickness, what are the angles, what is the suitable, and then we try to making the helmet based on the structure that we have. And in that helmet, they go under the BS, I mean the loading conditions. It was a dynamic load under the BS 6655, which is about the healthy of the helmet. And there is a different impact, like front, top, and the corner impact, but specifically in this test we're looking at the front impact, because that's based on the previous research, it's the 10 to 15% of the 80 to 90% of the damage is from the front. So that's what was the reason. But there was extra analysis for the back and for the side injury as well. So the outcome was showing that the corrugated compared to the solid structure, the corrugated structures are better in terms of the head injury, preventing the head injury based on the acceleration, and also looking at the dynamic part. It shows us that it's the corrugated structure, although it's got a little bit of the break because of the layers, but it works better than the solid structure. So just to conclude everything is as an engineer, I think there's a sustainable way to redesign the product. It's not a matter of which engineer, I mean, which part of engineering you are doing, you're electronic, you're mechanical, you're material, but there is a way. And we as an engineer, we have a responsibility to make the world a better place to live. Thank you for listening, and I am open for any question.
Thank you, Mahshid. Yeah, so let's check if there's any questions in the chat.
Just raise my hand.
Yeah. Serious, please.
Can I, just ask, just want a permission to ask a question if possible.
Yeah, sure.
Yeah,
thank you.
Go ahead.
So just thank you very much, Mahshid, for this interesting presentation. Just want to ask if you are planning to do any research to analyze the recyclable material, if you compare them with the new materials, according to the parameters that you mentioned, for example, the stiffness, or so is there any research which you can do, because you were mentioning recycle, of course, the 3 R's, the reuse and the recycle. So all these we need at the end, of course, to keep the performance how it was before. So are you planning to do any research to analyze the proposed recycled material?
Yes, Nagham, there are, I mean, the recycled material these days, it's a very big area. Like it's either using some material which was not recycled previously, so try to make them recycle or use them in a different application. For myself, I haven't gone through much in terms of the material side of which material is recyclable, or is there any possibility to reuse use instead of using some part which was not recyclable previously, but using some material that is recyclable. My research is mostly in using the structure and reducing the material rather than using a different material. But there are so many research and the research fund in that area to look at. I mean, there are some sort of a polymer which is not recyclable, but I mean, I attended previously in a conference where they are trying to shred them and use them again in the building applications or the construction applications. Yet there are so many research in that area going on, and it's a wide, really area of the research.
Yeah, thank you. And my last question: do you think the lightweight material can be mass produced?
It is a very good question, whether it's going to be mass, because the 3D printing is quite new, and there is a gap that we need to look and need to be educate the industry about that, because I was in the 3D printing a sort of a seminar, and the Rolls-Royce was mentioning that they use the 3D printing for their parts, and they could save 100. Previously they were using a different part and they joined them together, but after using the metal 3D printing, it happened that they could save 100. They could reduce 100 of the nuts and joints. So we are talking about 100 of the weight of the nut, 100 nuts which they sort of were producing the material. So they could reduce all of those material which is used. Regarding the mass production, it is a little bit time money consumption, because it's quite expensive, but the company need to be educated that they can reduce the employer then, because if you are reducing about 100 of joints, so you need at least 20 people to assemble them. But there is a need of education, so there is a future for it, but it's going to take a time.
Okay, thank you very much.
Thank you, Nagham.
Thank you for answering the question. Any other questions? I see there's a question in the chat from Ruth.
Yeah, really quick one. I love the diagram where you talked about the products failing and how they fail, which has actually reminded me of the kind of labs that we've been working with our kids at home in primary school, you know, kids of age 10 and so on, and they're doing Lego building bridges just to see how the different shapes and structures can hold more weight. Kids are learning a bit about this in school, and that's fantastic. But in computing, we have the idea of fail gracefully, that at some point it's going to fail, and we know it's going to fail at some point, but that they're designed to fail safely when it does happen. So I don't remember, I'm really intrigued by the talk, but I don't know if you mentioned that. So in the new structures that you're designing to be stronger and to be reusable, are you also considering graceful failing?
Yes, absolutely. Yeah, we are looking at the failure. It depends on the applications, what type of the failure. And sometimes even looking at the failure is not important, because looking at the experiment and sort of FEA, it shows us that this structure is very far from being a fail based on the applications. For example, when we were looking at them for the implants and we were applying the cyclic load, it was very, very sort of unlikely to fail. But looking at the airplane, when we were looking at sort of using it, the possibility of using it in the airplane, there was a possibility of the failure. And that's why we were looking at sort of reducing the area of this structure by having a panel structure, maybe some part at the middle, it's a solid structure, then the area. So if you look at the failure quite, because this is very important in engineering design, to looking at the failure and avoid the failure. And based on the what industry we are looking, there are different safety factors even to apply as well. So that's a very big part of the research that we do as well.
Thank you.
No worries.
Thank you. Thank you all speakers. I'm now sharing my screen. Yes. So thank you all the speakers for the wonderful presentation and answering the questions. So we will have the next event, the third early career talk on the 12th of December this year. So you're very welcome to join the third event. And I'm now handing over to Dr. Nagham for the closer. Go ahead, please.
Thank you. Thank you very much, Yao, and thank you very much, Odawuk, for organizing this workshop. This workshop for me, as I always say, it's a unique experience for our audience to witness talks from researchers who are not only from different universities. In this case, we've got from researcher from University of West London, Northumbria, Coventry University, and Belhaj Bushayb University. But also they all have different engineering background, built environment, biomedical, sound, and biomechanic. So that's really good to have this opportunity to look at other research and other different areas which we might not have the opportunity to look at. But also what I would like to mention that the one important feature of this early career talk is to make sure that we have international representation as researcher from outside the UK. So for example, this workshop, we've got 3 researchers from UK and 1 researcher, Dr. Kheira from Algeria. So this is something that we'd like to keep and continue with, just to point out the work that has been done by women in engineering outside UK. And today we clearly seen how the researcher then they can analyze the interesting outcome using different research tools, numerical equations, simulation, coding. So that also show you a variety of ways of analysis in the research field. So thank you so much for joining us in this interesting event. And we are calling for women in engineering and computing to give a technical and inspirational talk for our coming programs and sessions. For example, this program, as Yao mentioned, the next event will be on the 12th of December this year. And anyone from academia, researcher, or from industry who've got experience less than 10 years can apply for this interesting event. So thank you very much, and thank you very much, Ruth, for sharing with us this experience. Thank you.